All right, so welcome to STAT 313, lecture 21. So today we'll be discussing more on regression. So last time we started regression and we discussed a lot of different problems on regression and how to choose the parameters of regression. So today we'll be discussing some more functions on the regression and how we can understand things better based on that regression analysis. Okay, so let's get started. So today let's get started by an exercise problem from last time. So this is more on regression. Xi minus X bar. And what you have is where alpha hat is Y bar and beta hat, the statistic, the estimator is given by summation I from 1 to n yi xi minus X bar divided by summation I from 1 to n little xi minus X bar squared. Okay. So that is what we found in our discussion last time. Okay. Now, based on this one, so today the first problem is, so this is from the exercise. Um, 9.6.4. Okay. It's very simple. It says that show that the covariance between alpha hat and beta hat is 0. Okay. So let's get started with this one. So we are going to show that the covariance between alpha hat and beta hat is 0. So here is the solution. So here is the solution. So let's compute the covariance. So covariance of alpha hat and beta hat really means we are trying to compute the summation I from 1 to n yi and this quantity, right? So it's a summation I from 1 to n yi xi minus X bar summation I from 1 to n xi minus X bar squared. Okay. Note that whenever you see a little letter, so that means it's a known and y is a random variable here. Okay. So this from the we know that y1 y2, so we know that this is a sample, right? So y1 y2 etc yn, so they are independent. Okay. So if I did is this, so then what we'll have is the following. So this is going to be, you can pull out some of the numbers. So it's 1 over n, I'm pulling out this one, and then this summation I from 1 to n. So this is the first summation, and I have to pull out another summation, but I cannot call it I because then it will look same. So j from 1 to n, and then basically I have to multiply this two, the second one with also this quantity. So let's call this one equals to sx squared. So it's a known number, right? Because if I give you the values of x1, x2, xn, so this is known. So what I really have is here we have this xi minus xj minus x bar, because I'm calling the second index by j. So all these indices are changed to j. Let me just write it in more clearer term. So this is going to be covariance of 1 over n summation I from 1 to n yi. Let's move this to j index. So j from 1 to n yj xj minus x bar, and then I call this sx squared. That's a given number. Okay. And then this is nothing but using that this y1, y2, yn, so they're independent. So well, actually it's true irrespective of that. So it's 1 over n summation I from 1 to n summation j from 1 to n. What we had is y xj minus x bar over sx squared times covariance of yi yj. And now I'll be using that they are independent. So that means only the so the cross terms are 0. Only the like if it's yi that is non-zero, and all the other cross terms are 0 because we are using the fact that it's independent. So what we are doing is that using the fact that y1, y2, yn are independent, we have now covariance of alpha hat, beta hat. So this double summation, so converts to it just transforms to one summation, because a double summation means it has so suppose it's y1 and y2, so that covariance would be 0 because they're independent. And similarly, all the cross like if the index are different, then that will be 0. So only terms that will survive is say y1, y1. Okay, so it becomes 1 over n summation I from 1 to n, just one sum, xi minus x bar over sx squared, and covariance of yi. So whenever I equals to j, that is non-zero, otherwise it's 0. And what is this one? So it's a variance of y, right? So this is 1 over n summation I from 1 to n xi minus x bar sx squared, and this is variance of yi. Okay. And this expression, so now let's look at what is variance of yi. So this is something we wrote last time. So variance of E of yi is this one, and variance of yi is sigma squared. So this is really 1 over n summation I from 1 to n. So last time we see that E of yi is alpha plus beta xi minus x bar, and variance of yi is sigma squared. Okay, so that's what we use here. So it's xi minus x bar sx squared sigma squared. And that's pretty much it. Now, if we are just pulling out these constants, so this is 1 over, so sigma squared over n sx squared, summation I from 1 to n. We have seen it multiple times by now, xi minus x bar. So what we have seen multiple times is this quantity is 0. Okay? So this is 0. So what we found is covariance of alpha hat and beta hat is 0. Done. So this shows that when we are talking about this particular like alpha hat and beta hat, so we have the covariance 0. Okay, that that is a very important result, and now we'll move on to something else after this one. Okay, so we I mean after this one, so let's try to compute something else. So this new development, it depends on the fact that let's go back to the previous work. So what we have found so far is the following. I have written it before, but let me just write it again. So y hat equals to alpha hat plus beta hat x minus x hat, sorry, x minus x bar, right? So this is something we know. And we have also seen that so this is a fitted value. I wrote it right here. Also, what is E of y? So where y is y2, yn. So they are following this distribution for y, if I write that. So we have seen that it's alpha plus whatever the corresponding value is for x. So it's, I'm talking about this one. So say alpha plus beta x minus x bar. So if y is the response variable for the value x. So when we have, say, so what we, please note the difference. So this is the fitted value. Okay. So this is a fitted value for x. And what is, so here we have used alpha hat and beta hat. So here, alpha hat, beta hat used. Okay. And this is the expected value of the random variable y. So this here, the original alpha and beta used. Okay. So original alpha and beta from model. So there are different, these two are two different things. So for here, alpha and beta hat we have computed, but here alpha and beta are coming from the model, which we, we can of course estimate this best as alpha hat, but this is what it is. So here it's really speaking, it's alpha plus beta. So the first thing we'll be doing today is we are so number one, or let's call this A. We are interested in knowing the value of the expected, the mean response that is E of y. And for convenience, let's denote it by say mu sub y, or let's keep it mu of y for a given value of x of the predictor. Okay. In other words, we will try to compute the confidence interval for the mean. Okay. Please note that this is, this is not the same as a fitted value. So this is different. So here it's coming from the alpha and beta, which is the original. So far we have computed the confidence interval for alpha hat, for beta hat, but for this is something new. So we don't know the value of alpha and beta yet. And what we are doing is, so we are thinking this E of y as the expected response based on an x. We are trying to find a confidence interval of that. Okay. We'll be starting right with the theorem. So let's write this theorem down. It goes like this. 1 minus alpha 100% confidence interval for E of y is given by y hat. This is the fitted value I wrote. This is something we know. Plus or minus t of alpha over 2, comma, n minus 2, square root of MSE. We have discussed this last time. I'll write it again. Or 1 over n plus x minus x bar squared over summation xi minus x bar squared. Okay, so there are several things. So this x is a new variable and the data set is, so let me just make it precise. So here the data is really x1, x2, xn. Okay. So this x may not be a part of that one. So x bar is really 1 over n xi, I from 1 to n. Okay. So x can be one of these xi's or x can be something else. So in other words, this x may be something completely different. So we're just trying to compute the value corresponding to this one. By the way, since this MSc, so it was mentioned last time, let me just write it here. So here, the MSc is really given by n sigma hat squared over n minus 2. So this is the MSc. We have discussed this last time. So if you want to see how you implement this, so just refer you back to the lecture note 20. So last time we studied this. Okay, let's prove it. So I will be proving this result. So let's do the proof. All right. So first of all, recall that what are those alpha hat, beta hat, and other things. So alpha hat follows a normal distribution with mean alpha sigma squared over n. Beta hat follows a normal distribution with mean beta sigma squared. Again, we have done everything last time. So I would refer you back to the last class note. I from 1 to n xi minus x bar squared and n sigma hat squared over sigma squared follows chi-square distribution with degrees of freedom n minus 2 are independent. Okay, so this alpha hat, beta hat, and this quantity, they are independent. Therefore, we can write, so y hat is a linear combination of independent normal variable. Okay, so what is y hat? So y hat is given by alpha hat plus beta hat x minus x bar is a linear combination of independent normal random variables. Right, so this alpha hat is normal, beta has is normal, so you're taking the sum of two independent normal and they're independent, right? What is E of y hat? So E of y hat, well, it's basically the sum of this one, so it's E of alpha hat plus x minus x bar E of beta hat. So this is alpha. Why? Because we have seen it right here. Alpha hat follows a normal distribution, mean alpha. So this is alpha plus this is x minus x bar. And E of beta hat, we have seen that this is beta. Beta hat follows a normal with mean beta, right? What is this one? Now, if you look at that, this isn't it same as E of y? So look at this E of y. So this E of y is alpha plus beta x minus x bar, right? So this is what we found is this is really EY. We noted before EY is alpha plus x minus x bar beta. We have seen that. Okay. Okay. So we found that this y hat is follows with mean EY. Okay. First observation. Second observation. What's the variance of y hat? So once again, they're independent normal distribution. So it's going to be variance of alpha hat plus x minus x bar squared variance of beta hat because they are independent. Okay, and we have already seen that for alpha hat, its variance is sigma squared over n. Beta hat, it's this one, right? So we are going to write this as, so it's sigma squared over n plus x minus x bar squared. This is sigma squared over summation I from 1 to n xi minus x bar squared. Okay, so this, if I just simplify this, is sigma squared 1 over n plus x minus x bar squared over summation I from 1 to n xi minus x bar squared. Okay. And of course, it's a combination of independent, so it's a linear combination of independent normal random variables. So that means from here we can say y hat is following a normal distribution. Okay. And with the mean this one and variance this one. So y hat follows a normal distribution with mean E of y and variance this mess. So sigma squared 1 over n plus x minus x bar squared I from 1 to n xi minus x bar squared. Okay. Now, please note that whatever we have here, so all the expressions, we can, from here, I can compute that this y hat minus E of y over the square root of this one, xi minus x bar squared over summation I from 1 to n xi minus x bar squared. So I subtracted the mean divided by the square root of the variance. So this follows a normal distribution with mean 0, variance 1. Right? Okay, now originally we have seen that this alpha hat, beta hat, and this they are independent. So if I use that fact now, so let's define a random variable t by taking the standard normal distribution as a numerator, ey over. So let me just simplify this one. So sigma is coming out, or it doesn't really matter. So I'll just keep it here. Sigma squared 1 over n plus xi minus x bar squared summation xi minus x bar squared I from 1 to n. And I'll divide by a chi-square distribution with appropriate degrees of freedom. Okay, so we know that we have seen that this n sigma hat over sigma square, it follows chi-square n minus 2, right? And it is independent with whatever we have done so far. Okay, so I can write this, I can divide by the square root of the chi-square distribution. So we have 1 sigma n sigma hat squared over sigma squared, and I'll divide by the degrees of freedom that it's n minus 2. So then we know that it follows a t distribution with the same degrees of freedom, n minus 2. So this is the t distribution with n minus 2 degrees of freedom. Standard normal over square root of the chi-squared over degrees of freedom, and they're independent, so that got to be a t squared, the t distribution. Okay, and hence from the standard as like computation of the t distribution, we know the probability that this quantity, I mean, if we can simplify this a little bit, right? So we can basically we can write that therefore. So if I write this quantity a little bit, y hat minus e of y. Let's see. Let's put everything in the denominator. So this one, so MSE is n sigma hat squared over n minus 2. So this one is really the MSE, right? So I can write this as over square root of MSE, and this sigma squared and sigma squared cancels. And then we have square root of 1 over n plus x minus x. Sorry, this is not xi. There should not be any xi. Yeah, it was just x. Okay, so x minus x bar squared summation I from 1 to n xi minus x bar squared. Okay, so this follows t of n minus 2. After simplification. Okay, and what does it mean? So if something follows the t distribution, so that means really the probability of if we want the confidence interval 1 minus alpha. So the probability that this quantity y hat minus e of y over square root of MSE and then square root of 1 over n plus x minus x bar squared over summation I from 1 to n xi minus x bar squared. So this is less than t of alpha over 2 n minus 1 minus t of alpha over 2 n minus 1. So that is 1 minus alpha, right? So after simplification, so you can get that. So the 1 minus alpha 100% confidence interval for E of y is if you just compute this one, so this is really y hat plus or minus t of alpha over 2 n minus 2 n minus, sorry, MSE x minus x bar squared summation I from 1 to n xi minus x bar squared. Okay. So if we observe the fitted value, so y hat equals to little y hat, then we get little y hat. So that's just a, so this is a random variable, and this is just a particular value, alpha hat over 2 n minus 2 square root of MSE 1 over n plus x minus x bar squared I from 1 to n xi minus x bar squared. Done. So we proved that this is the confidence interval for the for E of y. Okay. Let's do an example based on this one. So here is an example. Example. So this example is based on the eruptions of the Old Faithful geyser in Yellowstone National Park. It is pretty regular. Okay, so actually, I'll show you the data, but rangers, they post the predicted time until the next eruption. So that is the y in minutes based on the duration of the previous eruption. That is x in minutes. So if maybe the previous eruptions was for 3.4 minutes, and then the next eruption can be maybe 2.9 minutes. Okay, so x is the observed variable, y is something we should try to predict. So using data collected on 107 eruptions by some geologist, and the name of the geologist was R.A. Hutchinson. What is the mean time? And this is the mean time until, and mean time is in the so the y variable. So until the next eruption if the previous eruption lasted for 4.8 minutes. So let's compute this. Now I'll show you the data set. So the data set you can let me share my screen. So here is the data. Okay, so I'll post it online pretty soon. But if you want to have a look, so here basically we have the time until the next eruption. So this is the time in minutes until the next eruption, and this is the duration of the previous eruptions. Okay, so that means we are trying to predict these y values based on these x values. And this is the data set. Okay, once again, I'll be posting it, so don't worry. Now the question is, if we know the previous eruption lasted for 4.8 minutes, how much time do we have to wait until the next eruption? And this is not just how much time. What is the mean time until the next eruption? Okay, so it's a classic setting for what we discussed. For the what we have discussed until this point. So let's compute this. So here is a solution based on the data. So let's denote the y variable. So y equals to what we are really predicting. So it's given by y hat equals alpha hat plus beta hat x minus x bar, right? Now, based on the computation, or based on we can easily show that it can be shown. We have already seen how to compute alpha hat, beta hat, and x bar, right? So compute values of alpha hat, beta hat, and x bar based on the formulas as provided in the last class and even today. Okay. At the very beginning, we have seen these formulas for alpha hat is y bar, beta hat is this one, so we can always compute this, right? Now, what we want to do is, so basically it can be shown that this y hat is given by 33.828 plus 10.741x. If you simplify this, you get this. Now for x equals to, so we are trying to compute the time until the next eruption when we are given that, let's see. So I'm just trying to find the problem. Oh, here it is. Here it is. So it's 4.8 minutes, right? So 4.8, then the corresponding value of y hat is little y hat, which is 33.828 plus 10.741 times 4.8. If you compute this, it's 85.385. So that's my little y hat. So that is my that's my observation. Okay. Now the formula that we are going to use is this one. So this is my confidence interval. Okay. So what do you need? So we need to compute, say, the MSE. Okay. How do we compute the MSE? So it's basically n times sigma hat squared over n minus 2, right? So let's compute this. So in our data set, what is n? So there are for our data set, n equals to 107. So I can compute that MSE, which is n sigma hat squared over n minus 2. How do you compute it? So it's basically 107 over 105 and sigma hat squared. And this is something we have provided an expression last class. So it's a expression found in last class. So given a set of data, you can always compute this. And for this particular data set, if you compute it and if you round it, you'll get it as 44.66. All right. So now, what about the other two? So we are done with y hat. We are done with MSE. So n we know. So x minus x bar squared. So x bar also I can compute. So this is very easy to compute. X bar is the average of all the x's which are provided. It's a 3.46075. And therefore, summation xi minus x bar squared, it's from the data, I from 1 to n. And in this case, n is 107. So that if you compute, it's 113 from 835. So I'm just listing you all the numbers, but you can check it from the actual data set. Okay. So together, so and also, so we want say 95% confidence interval. So let's see. We can see that T of say alpha value is 0.05 for the 95% confidence interval. So T of alpha over 2 n minus 2. So that is really T of 0.025 and 105. Right? So that's value is 1.9828. Hence, putting everything together, we get the confidence interval for the mean time until the next eruption if the previous, let's just write if x equals to 4.8 is given by, well, so we have all these numbers. So the first number is 85.385. I'm basically using this formula. So y hat plus or minus this one. Okay. So it's going to be 85.385 plus or minus 1.9828 square root of 44.66 and then 1 over 107 plus 4.8 minus 3.46075 squared over 113.835. Yeah. This number, 113.835. If you compute this, you'll get 85.385 plus or minus 2.099, which is 83.286 to 87.484. So actually, when we are waiting until, if the previous eruption was lasting for 4.8 minutes, we have to wait between 83.286 and 87.484, that many minutes, until we get the next eruption. Okay, so that is the answer based on the 95% confidence level. Okay, so this is the 95% confidence interval for the mean that we wrote as E of y. Okay. All right. So this is how things are computed. Now let's finally let's end with another very interesting thing. So here, what we are doing. So what we have done. So remember, I wrote here topic A. So topic A was we are trying to compute the confidence interval for E of y. Let's do the second topic. So it's topic B. Okay. Now here it's a little different. So instead of finding the confidence interval for the mean, if you're so if we are interested in knowing the value of a brand new observation, say y sub n plus 1, because we already have fitted yn, but this is a new one for a given value x of the predictor. Okay. So that is what we are interested in knowing the value of a new observation yn plus 1 given the value of x as a predictor. Okay. We will try to calculate a prediction interval for the new observation for yn plus 1. Okay. A confidence interval for yn plus 1. That's a little different. The previous one was, we have, so we are trying to estimate the value of E of y, so expected value of y, and we are trying to get an interval for that one. And here it's not expected value of y. Here's a new value of y, and we are trying to get the estimated value for that, okay, or the interval for that. Okay, so now how do we do it? So let's straight away write the result. Sorry, I'm trying to make my camera work. Okay. So here is a theorem. It goes like this. 1 minus alpha 100% prediction interval for a new observation yn plus 1 when the predictor x equals to xn. So let's use a new value of xn plus 1 so that we can just ignore the first. So it's just new value. Okay, so it's not really one of those old values. It's given by yn plus 1 hat, an observed value of that, plus or minus t of alpha over 2 n minus 2 square root of MSE. Up to this, it looks everything same as before. And even the last part, it looks very similar to before. Xn plus 1 minus x bar squared. Here it's I from 1 to n, xi minus x bar squared. So if you look at this one and then plus 1. That's the only thing is this one is the addition. So look at the previous one. So forget about this y hat and yn plus 1. So both are like the thing that we're trying to compute. So here the observed value of y is the y hat. Based on that, we are trying to have a estimated interval for e of y. And here the observed value is yn plus 1 hat. So based on that, we are trying to uh, have an interval. So have a confidence interval for this this yn plus 1. Okay, let's do it. And everything else is the same except for that one. So here's a proof. Okay. So let's recall that what is yn plus 1? How do you compute yn plus 1? So last time we have seen that, I mean, we have this equation, right? So I'm trying to show you the equation for yi. So yi is really following a normal distribution with the mean alpha plus beta xi minus x bar and sigma squared. Okay. So that means, I mean, if I'm just writing this for a new observation, so this is for a new observation n plus 1, y of n plus 1, this is going to be alpha. Well, just let me just clarify this one more thing. So here, before even writing this one, so this is true for I from 1, 2, 3, n, right? And then what do we have? So forget about the new observation. So it's for the old observation, right? So this is how we model. And then we write yi equals to alpha plus beta xi minus x bar plus ei, right? Once we derive this one, or once we have this model, then let's call our regression model is obtained by interpolation. So what we do is the following. So after this one, we call, say, simply y instead of yi, just write y, and alpha plus beta instead of xi, just call it x minus x bar plus ei. Okay. So essentially, so we are assuming that, I mean, it's true. Previously, it was true for x1, y1, x2, y2. So it was true for those one. Now we are interpolating this to this one. But now let's look at this one. So this y still follows. So this EIs, I mean, so EIs are the so error terms, right? So this EI becomes E. So E is a normal distribution with mean zero variance square. So Y in effect, it follows normal distribution with the values with the parameter values alpha plus beta x minus x bar and the variance sigma squared. Okay, so it's the interpolated version. Okay, based on x1 y1 x2 y2 xn yn. The advantage is now you don't really need this x to be something like those x1 x2 xn. Okay, it can be just anything. Okay, so that's our new version. So based on the previous model, we'll be sticking to this one. So for predicting new value, so we can use this for predicting any x under regression model. So I can just have a value of x and then we can compute. Let's see. I mean, it doesn't really change much of anything in the previous discussion. So let's see what we can have. So we can write, first of all, therefore, we can write this y of n plus 1, that's for a brand new observation. It follows alpha plus beta xn plus 1 minus x bar and sigma squared. Also, from before, in alpha hat follows normal, beta hat follows normal, xi minus x bar squared, and this is something we wrote before. Okay. So another way of writing this is n minus 2. If I just multiply by n minus 2, so it's n sigma hat squared over n minus 2, right? Over sigma squared. And this is the MSE, right? So it's n minus 2 MSE over sigma squared. So this follows chi squared n minus 2. All right. So now these three are independent. So this is a new information. And these three are the old. Okay. Now let's consider, so this yn is the actual value, which we're really hoping for xn plus 1. Now let's compute, say, define, say w, which is y of n plus 1 is the actual value of this new observation minus the predicted value. By actual value, I mean that here the error term is included, but we have no control over the error term, so we cannot really know what it is. So we can really compute before that. So that is the predicted one, right? So this is going to be y of n plus 1 minus. So how do you predict this one? So basically, when you do the prediction, so really speaking, so you just use the maximum likelihood estimator, right? So y hat predicted value y hat can be really alpha hat plus beta hat x minus x bar. From here, we have no control over the error, so we don't touch it. So it's alpha is replaced by alpha hat, beta is replaced by beta hat, then that's it. Right? So this for y of n plus 1, so it will be alpha hat minus beta hat x of n plus 1 minus x bar. Right? So this is a linear combination of independent normal variable. Why? So this is normal. This is normal. And this is normal. By the way, I'm assuming that we can, we can show this y of n plus 1 is independent to alpha hat, beta hat, and n sigma hat squared over sigma squared. Why? Because these are only depends on y1, y2, yn. Okay, and this yn plus 1 is a sample, which is the next one, right? So and using the assumption of the independence of the samples, we can we can see that this yn plus 1 is independent of this one. Okay. All right. So now, so that means this follows some normal distribution. What is the expected value? So E of W would be E of y of n plus 1 minus E of alpha hat minus xn plus 1 minus x bar E of beta hat. We know alpha hat, we know beta hat, and we know E of y n plus 1, which is this one, and I'll leave the computation to you. It's really alpha plus beta xn plus 1 minus x bar. So for this one, minus alpha for this one, minus xn plus 1 minus x bar times beta, which is 0. So E of w is 0. Okay, and variance of w is going to be variance of yn plus 1 minus alpha hat minus beta hat xn plus 1 x bar. So all these are independent normal. So that means if you're using the independent normals, so it's basically variance of yn plus 1 plus variance of alpha hat plus xn plus 1 minus x bar variance of beta hat. Okay, which you can easily compute. It's really not that hard. It's given that all the information that we have. So this is really, if you use all the information, so it's a sigma squared. This is sigma squared over n, and here variance of beta is sigma. So it's x minus. Sorry, the last term should be squared here. So it's x n plus 1 minus x bar squared. And variance of beta hat is sigma squared over the summation I from 1 to n xi minus x bar squared. So that means if I compute this, it's sigma squared 1 plus 1 over n plus the rest xn plus 1 minus x bar squared summation I from 1 to n xi minus x bar squared. Okay, so that means w is normal, not only normal, it has mean 0, and variance is this thing. So it is sigma squared 1 plus 1 over n plus xn plus 1 minus x bar squared over I from 1 to n xi minus x bar squared. Good. Therefore, if I just divide that, so if I write the w minus 0 over that square root of sigma squared of this whole mess, 1 plus 1 over n, plus, now I'm tired of writing this thing, xn plus 1 minus x bar squared over summation I from 1 to n xi minus x bar squared. This follows a normal distribution, mean 0, variance 1. Okay. Define just like before. So there's a standard normal distribution. So define this w. So remember what is w? So w was really yn plus 1 minus yn plus 1 hat. Define this yn plus 1 minus yn plus 1 hat over this whole thing. Sigma squared 1 plus 1 over n plus xn plus 1 minus x bar squared over summation I from 1 to n xi minus x bar squared. So this is the numerator z, and I need something which is independent to this one, which is n sigma hat squared sigma squared over n minus 2. That's the chi-square. So this is the chi-square. We divided by degrees of freedom. So that means it is really following t minus. So t distribution with degrees of freedom n minus 2. And this, if you simplified, you'll get something like this one with the MSE, yn plus 1 minus yn plus 1 hat. And if I want to see in terms of MSE, so it's MSE, sigma squared gets cancelled. So this is square root of 1 plus 1 over n plus yxn plus 1 minus x bar squared, summation I from 1 to n xi minus x bar squared. Okay, so this follows t of n minus 2. Okay. Just like before, So we have done this one time, so let's do it one more time. Hence, we can find the confidence interval. So probability of something which is equal to 1 minus alpha would be, so let's write the variable. It's y of n plus 1 minus y of n plus 1 hat over square root of MSE. Okay. So 1 plus 1 over n plus xn plus 1 minus x bar squared, summation I from 1 to n xi minus x bar squared. So it got to be less than t of alpha over 2 n minus 2, because we have the significance level alpha, bigger than minus t of alpha over 2 n minus 2. Okay. In other words, so 1 minus alpha 100% prediction, its prediction interval for y n plus 1 hat is, well, yn plus 1, sorry, is, so this is basically the value that is the correct value. So that is given by yn plus 1 hat plus or minus t of alpha over 2 n minus 2 square root of MSE 1 plus 1 over n plus xn plus 1 minus x bar squared, summation I from 1 to n xi minus x bar squared. Okay. So for yn hat bar equals to, so suppose we compute this value and we know this value. So this is given by yn plus 1 hat, so that's the computed one, plus or minus t alpha over 2 n minus 2 square root of MSE 1 plus 1 over n plus xn plus 1 minus x bar squared, summation I from 1 to n xi minus x bar squared. That's it. So that is what we were trying to prove, and we proved it. Just a follow up, just to finish up this last example. So example, in the last example, for the old faithful geyser in Yellowstone National Park, what we're trying to find here is the following. What is the predicted time? Please note that it's not the average time. It's not the expected value. It's a predicted time until the next eruption if the previous eruption lasted for 4.8 minutes. It's the same thing that we did in the last problem, but here with a different approach. So here it's a predicted time. Okay, so last time what we did is, so we had a very similar problem, but we had the mean time. Okay, so we are talking about what is the mean time until the next eruption for the last problem, and here it's what is the predicted time until the last eruption. So it's not the average. Okay, okay. So let's come. So while computing this, so here is the solution. Last time we found that the regression equation is y hat is 33.828 plus 10.741x. Okay. So once again, little y hat for x equals to 4.8, little y hat is basically 85.385. Now, MSE, it's 44.66. We have found it last time. Okay. And also this summation I from 1 to 107 xi minus x bar squared equals 113.835. So this is everything we have found last time. Okay. And also with the alpha, so significance level 5%. So it's alpha over 2 n minus 2 is really t of 0.025, 105, which is once again 1.9828. Everything from the last problem carries forward. Okay. So putting together, we get the predicted time. So this is the prediction part. So the predicted time until the next eruption, if x is 4.8, is given by 85.385 plus or minus 1.9828 squared. Everything looks very similar to what we had last time, except now here we have 1 plus 1 over 7 plus 4.8 minus 3 point, by the way, so I forgot to write, so x bar is also 3.46075 for this data. So 3.46075 squared over, we have computed this 113.835. Okay. If you compute this, it's going to be 85.385 plus or minus 13.416, which is same as the interval 71.969 and 98.801. Okay. Now I would like you to see the difference. So last time it was basically, so let's look at the previous results. So it was the average was between 83.286 to 87.484, but now we are getting a much bigger interval, and typically it's the case. So for a given value of x for the predictor, the prediction interval for a new observation is always longer than the corresponding confidence interval for the mean. Okay, so that's because there is an extra term. So if you look at that, so we have this one. So that's why this is typically always the case. And let me just conclude by this observation. So for a given value of x of predictor variable, and a confidence level 1 minus alpha, the prediction interval for a new observation yn plus 1 is always longer than the corresponding confidence interval for E of y. Okay, so this is because of that extra one. Okay, so that extra term. So we have this one plus something, because otherwise it's a confidence interval. Okay, so that's because of that, right? So we with this we understand the regression, and we have done various problems based on this regression analysis. So that is all about it. So thank you very much. If you have any question, please send me an email. Okay, thank you.